On the 28th of April 2021, a spacecraft the size of a small car crossed a boundary that no human object had ever crossed in the history of our species. It flew into the atmosphere of the sun, not near it, not past it, into it. For 5 hours it was inside the solar corona, surrounded by plasma at more than 1,000,000 degrees, and then it came out the other side, still alive, still transmitting, carrying data that nobody on Earth had ever held before. And the first thing that data confirmed is a problem that has been sitting at the center of solar physics for 83 years, and which, on the face of it, should not be possible. The surface of the sun is around 5,500 degrees Celsius. The atmosphere above that surface, the corona, is between 1 and 2 million degrees, sometimes more. Which means as you move away from the sun's heat source, away from the furnace, out into empty space, the temperature does not drop. It rises. It rises by a factor of 200, sometimes 500. Heat is flowing from a colder region to a hotter one, and that is the direction heat is not supposed to go. Imagine standing next to a bonfire, and as you walk backwards away from it, you start to burn. That is the sun. That is what it has been doing above our heads every single day of your life, and until very recently, we had no idea why. The spacecraft is called Parker Solar Probe. On the 24th of December 2024, it flew to within 6.1 million kilometers of the solar surface, traveling at 692,000 kilometers per hour, which makes it the fastest object human beings have ever built. And what it has found in the corona is not what anyone expected. Today we go through all of it. What it actually means to touch the sun, how a spacecraft survives a place that vaporizes rock, the strange, twisted structures it discovered in the solar wind that nobody predicted, and why the answer to the oldest question in solar physics turned out to be hiding in a place we were already looking at. No hype, no filler, just what the instruments recorded and what it means. Quick thing before we start. Drop a comment. What is the single most extreme place in the solar system you would want a spacecraft to go if cost and physics were no object? Inside Jupiter? Under the ice of Europa? Down into a volcano on Io? Tell me. I read all of them, and the answers are always more imaginative than the ones NASA can afford. If you want to be here when the next set of solar results lands, subscribe. It costs you nothing. A thumbs up genuinely pushes this to people who would otherwise never see it. So let us aim for 5,000 on this one. Now, let us get into it. To understand why this mission matters, you have to start with a man who was told he was wrong. In 1958, a young physicist at the University of Chicago named Eugene Parker wrote a paper. In it, he argued something that sounded to most of his colleagues faintly ridiculous. He proposed that the sun is not simply sitting there radiating light. He proposed that the sun is continuously leaking, that its outer atmosphere is so hot that it cannot be held down by gravity, and that it is therefore constantly blowing outward in a supersonic stream of charged particles in every direction, filling the entire solar system and washing over every planet in it, including this one. He called it the solar wind. The paper was sent out for peer review at the Astrophysical Journal. Both reviewers rejected it. They did not merely disagree with the conclusion. They regarded the whole idea as not worth publishing. The consensus at the time was that the space between the planets was essentially empty, a clean vacuum, and here was a postdoc claiming it was full of supersonic plasma streaming out of the sun at hundreds of kilometers per second. The editor of the journal was Subrahmanyan Chandrasekhar, one of the great physicists of the 20th century. Chandrasekhar read the reviews, read the paper, and could not find an actual error in Parker's mathematics, so he overruled both reviewers and published it anyway. 4 years later, in 1962, NASA's Mariner 2 spacecraft flew toward Venus carrying instruments that measured the space it traveled through. It found a continuous stream of charged particles flowing outward from the sun at exactly the sort of speeds Parker had calculated. He was right. He had been right the entire time. Eugene Parker lived long enough to see something no scientist had ever seen. In August of 2018, at the age of 91, he sat at Cape Canaveral and watched a Delta IV heavy rocket lift off carrying a spacecraft named after him. It is the only time NASA has ever named a mission after a living person. He died in March of 2022 at 94, after the probe had already flown into the corona. He got to see it. He got to see his own theory confirmed by a machine that carried his name into the thing he had spent his life explaining. Now, let us talk about the problem that spacecraft was built to solve, because it is genuinely strange and it is worth understanding properly. The sun generates its energy in the core through nuclear fusion at around 15 million degrees Celsius. That energy then takes an absurdly long time to work its way outward, bouncing between atoms, being absorbed and re-emitted over and over, before it finally reaches the visible surface, the photosphere, which sits at about 5,500 degrees. That is the bright disk you see. That is the part that gives us daylight. Above the photosphere is a thin layer called the chromosphere, and above that is the corona, which extends millions of kilometers out into space. You have almost certainly seen it. During a total solar eclipse, when the moon covers the disk, that ghostly white halo streaming out around the black circle is the corona. It is the sun's outer atmosphere. And the corona is between 1 and 2 million degrees Celsius. Read that again in the correct order. The core is 15 million degrees. The surface is 5,500. And then the atmosphere above the surface, further from the core, further from every source of energy, is 1 to 2 million degrees. The temperature drops by a factor of nearly 3,000 from the core to the surface, exactly as you would expect. And then it climbs back up by a factor of 200 or more for no reason that classical physics can explain. The energy is going the wrong way. Something in the corona is being heated by a mechanism that is not simple radiation from below, because simple radiation from below cannot do this. This is called the coronal heating problem, and it has been the single biggest unsolved question in solar physics since it was first properly recognized in the 1940s. There have been two leading families of explanation, and physicists have argued about them for decades. The first says the answer is waves. The sun's magnetic field lines behave a bit like guitar strings that are anchored in the churning, boiling surface. As the surface convects, it plucks those field lines, sending waves traveling up along them into the corona. These are called Alfvén waves, and if they carry enough energy and then dissipate it in the right place, they could dump heat into the corona from below. The second says the answer is reconnection. The sun's magnetic field is not tidy. It is a tangled, knotted, constantly shifting mess, and when oppositely directed, magnetic field lines are pushed together, they can snap, break, and reconnect into a new configuration, releasing an enormous burst of energy in the process. Do this constantly on small scales all over the sun, and you get what is sometimes called nanoflares. Millions of tiny explosions everywhere, all the time, cooking the corona. For decades, we could not distinguish between them. Because to distinguish between them, you have to go there. You have to put instruments inside the corona and measure the magnetic field and the particles directly, in the place where the heating is actually happening. Everything else is inference from 150 million kilometers away. So NASA built a spacecraft to go and stand in the fire. And this is where it gets genuinely impressive from an engineering point of view, because the obvious question is the right one. How does anything survive that? The answer is a piece of hardware called the thermal protection system. It is a shield about 2.5 meters across and roughly 11.5 centimeters thick. It is made of 2 sheets of carbon-carbon composite, sandwiching a core of carbon foam that is about 97% air, which makes the whole thing astonishingly light for its size, around 73 kilograms. The sun-facing side is coated with a specially formulated white alumina ceramic, chosen to reflect as much light as possible. In the closest approaches, the face of that shield reaches roughly 1,377 degrees Celsius, hot enough to melt steel, hot enough to glow, and directly behind it, in the shadow it casts, the spacecraft's instruments sit at around 30 degrees Celsius. Room temperature. A comfortable spring afternoon, 11 centimeters away from something hot enough to destroy most metals. Now, how is that possible when the corona is 1,000,000 degrees and the shield is only reaching 1,300? Because temperature and heat are not the same thing, and this is the single most misunderstood point in this entire story. Temperature measures how fast particles are moving. Heat measures how much energy actually gets transferred into an object. And the transfer depends on how many particles there are to do the transferring. The corona is astonishingly hot, but it is also astonishingly thin. It is a near vacuum. The particles in it are screaming along at speeds corresponding to 1,000,000 degrees, but there are so few of them that they can barely deposit any energy into anything. The everyday analogy is an oven. If you set your oven to 200 degrees and put your hand inside, into the air, you can hold it there for a moment without injury. If you touch the metal rack at the exact same temperature, you burn instantly. Same temperature, wildly different heat transfer because metal is dense and air is not. The corona is the air, taken to an extreme. Parker Solar Probe is not being cooked by the corona's temperature. It is being cooked by the raw sunlight, which at closest approach is around 475 times more intense than it is here on Earth. That is what the shield is for. The shield is fighting the light, not the plasma. And to get there, the spacecraft had to do something counterintuitive. Falling into the sun is not easy. Earth is orbiting the sun at about 107,000 kilometers per hour sideways, and anything launched from Earth inherits that sideways motion. To get closer to the sun, you have to shed that sideways speed, and that takes enormous energy. So Parker uses Venus. It has performed a series of 7 gravity assists at Venus, each one bleeding off a little more of its orbital energy and dropping its closest approach a little nearer the sun. Each flyby tightens the noose, which brings us to the 28th of April 2021, and the day the phrase touching the sun stopped being a metaphor. Here is the immediate problem. The sun does not have a surface in the way Earth does. There is no ground. There is no line where the sun stops and space begins. The photosphere is just the depth at which the plasma becomes transparent enough for light to escape. So what does it actually mean to enter the sun's atmosphere? Where is the edge? Physicists define it with something called the Alfvén critical surface. Close to the sun, the solar plasma is dominated by the sun's magnetic field. The plasma is magnetically bound to the sun. Waves traveling through it can move faster than the plasma itself is flowing, which means information and pressure and material can still travel back down toward the sun. The sun still has a grip on it. That region is meaningfully part of the sun. At some distance out, the outflowing plasma accelerates until it is moving faster than those waves can travel back. Past that point, nothing can return. The material has broken free. It is no longer part of the sun's atmosphere. It is now the solar wind, gone forever into the solar system. That boundary, where the flow speed exceeds the Alfvén wave speed, is the Alfvén critical surface. It is the outer edge of the sun. It is the closest thing the sun has to a shoreline. On the 28th of April 2021, Parker Solar Probe crossed it at roughly 18.8 solar radii, about 13 million kilometers from the center of the sun. And its instruments recorded the change directly. The magnetic field conditions and the plasma behavior flipped into the regime that only exists inside the corona. The spacecraft was, in the only definition that means anything physically, inside the sun's atmosphere. NASA announced it in December of 2021. For the first time in history, a human-built object had touched the sun, and the crossing itself immediately taught us something nobody had expected. Parker did not cross the boundary once, cleanly, like a plane entering a cloud bank. It crossed in and out multiple times, which tells you the Alfvén surface is not a smooth sphere. It is wrinkled. It is corrugated with spikes and valleys in structure, and Parker went weaving through them. That is not a footnote. It means the sun's outer edge is dynamic and lumpy in ways no model had drawn, and it hints that the solar wind is not being released smoothly but from specific structures. And that leads directly into the strangest thing Parker found: switchbacks. From its very first orbits in 2018 and 2019, the spacecraft's magnetic field instruments recorded something bizarre. As Parker moved through the solar wind, the magnetic field would suddenly, violently reverse direction, flip completely backwards, hold there for anywhere from seconds to hours, and then snap back to its original orientation. And this was not rare. It was happening constantly. The closer the spacecraft got to the sun, the more of them there were. Picture the magnetic field lines flowing out from the sun as ropes stretching into space. Now imagine that all along those ropes, S-shaped kinks are traveling outward, like the wave you send down a garden hose when you flick your wrist. The field doubles back on itself, then straightens out. That is a switchback. Nobody predicted them at this abundance, and crucially, they were carrying energy. Inside a switchback, the solar wind was measurably faster. Something was injecting bursts of energy into the wind, so the question became urgent. Where do they come from? Because if you can find the source of the switchbacks, you have quite possibly found the mechanism that heats the corona and accelerates the solar wind, and you have solved the 80-year problem. In June of 2023, a team led by Stuart Bale at the University of California, Berkeley, published a paper in the journal Nature that traced them. They used Parker's data from close-in passes and worked backwards, mapping the fast-moving particles and the magnetic structures back down to their origin on the solar surface. And the switchbacks did not come from just anywhere. They mapped back to specific locations. They came from the edges of supergranulation cells. The sun's surface is covered in convection cells, enormous churning bubbles of plasma rising, spreading, cooling, and sinking, like the surface of a pot of boiling soup viewed from above. Supergranules are the large-scale version of these, roughly 30,000 kilometers across each. And at the boundaries where these cells meet, where the plasma is sinking back down, the magnetic field gets concentrated, funneled, and squeezed together. And in those funnels, magnetic field lines of opposite orientation are pushed into each other. And they reconnect. They snap and reform, releasing energy and firing a kink up the field line. Bale's team argued that the fast solar wind is powered by magnetic reconnection in these funnel structures, and that switchbacks are the fingerprint of that process, propagating outward. Which means the argument between waves and reconnection, the argument that ran for decades, tipped. Not settled, and I want to be precise here, because it is not fully settled and no honest researcher will tell you it is. But the evidence from inside the corona pointed hard at reconnection as the dominant engine of the fast solar wind. The answer to the coronal heating problem was not sitting in some exotic unknown mechanism. It was sitting in the magnetic knots at the edges of the boiling cells on the surface of the sun, a place we have been photographing for a century, and it took flying into the corona and reading the field directly to see it. Now to the record. On the 24th of December 2024, Parker Solar Probe made its closest approach yet. 6.1 million kilometers from the solar surface, 3.8 million miles. To give that a scale, if you shrank the distance from the Earth to the Sun down to the length of an American football field, Parker would be about 4 feet from the end zone. And to get that close, it was moving at 692,000 kilometers per hour, 430,000 miles per hour. That is roughly 190 kilometers every second. At that speed, you could travel from New York to Tokyo in under a minute. It is about 0.06% of the speed of light, and it is, by a wide margin, the fastest velocity ever achieved by anything human beings have made. During that pass, the spacecraft went completely dark. It was too close to the sun to communicate, and the entire mission team at the Johns Hopkins Applied Physics Laboratory had to sit through Christmas Eve and Christmas Day with no way of knowing whether their spacecraft still existed. On the 26th of December, a beacon signal came through. It was alive. It was operating normally. It had gone deeper into the sun's atmosphere than anything ever built, and it had come back out. Now let us be honest about what all of this does and does not mean, because this is where you deserve straight talk rather than a triumphant ending. Parker Solar Probe has not solved the sun. The coronal heating problem is not closed. What Parker has done is take a question that was purely theoretical, where competing models could not be distinguished because nobody had ever measured anything from the inside, and it has supplied hard in situ data that strongly favors one family of explanations over another. It has shown that magnetic reconnection near supergranule boundaries is doing serious work. It has not proved that waves do nothing, and most solar physicists still expect the true picture to involve both, in different proportions, in different regions, at different times. It also has not touched the sun in the way most people picture when they hear that phrase. It did not skim a surface, it did not dip into anything liquid or solid, because there is nothing liquid or solid there to dip into. It crossed a boundary defined by plasma physics. That is a less cinematic image than the headline suggests, and I would rather you have the accurate one, because the accurate one is more interesting anyway. And it has not made the sun safe. Which brings me to the part of this that actually affects you. Because the reason we spend $1.5 billion flying a spacecraft into the corona is not curiosity alone. It is infrastructure. The solar wind, the thing Eugene Parker was mocked for proposing, is not gentle. It carries the sun's magnetic field into the solar system, and when the sun launches a coronal mass ejection, 1 billion tons of magnetized plasma thrown outward at millions of kilometers per hour, and that ejection is pointed at Earth, it slams into our magnetic field and shakes it. In 1859, an event now called the Carrington event did exactly that. Telegraph systems across Europe and North America failed. Some telegraph operators reported receiving electric shocks. Some machines kept transmitting after being disconnected from their power supplies, running purely on the current induced in the wires by the geomagnetic storm. Aurorae were seen in the Caribbean. In 1859, the entire electrical infrastructure of human civilization was a few thousand kilometers of telegraph wire, and it was enough to catch fire. In 1989, a considerably smaller storm knocked out the Hydro-Quebec power grid in 90 seconds and left 6 million people without electricity. We now have a civilization built on continent-spanning power grids, on satellite constellations that run navigation and timing and communications, on undersea cables and transformers that take months or years to replace. A Carrington-class event today would not be an inconvenience. Every serious assessment of it is uncomfortable reading. We cannot stop it. What we can do is predict it, and by hours of warning. And hours is enough to shut down and protect the most vulnerable parts of the grid. And you cannot predict what you do not understand. Understanding how the corona is heated and how the solar wind is launched is not an abstract exercise in stellar physics. It is the foundation of the entire discipline of space weather forecasting. That is what Parker is for. If this was useful to you, share it with someone who thinks the sun is just the thing that comes up in the morning. Leave me a comment with the most extreme place you would send a probe and why. And subscribe, because Parker is still flying and still returning data from inside the corona, and the results are not finished. Now, if you want to go deeper, stay with me, because there are several things Parker found that did not fit the main story and that I think are genuinely wonderful. The first is the dust. The inner solar system is not empty. It is filled with a fine haze of dust, the ground-up remains of asteroids that collided and comets that shed material as they swung past the sun. That dust is what produces the zodiacal light, the faint pyramid of glow that you can occasionally see on a very dark night just after sunset or before sunrise, if you have escaped the light pollution. Back in 1929, a researcher predicted that this dust could not extend all the way to the sun. At some point, the solar heat would simply vaporize the grains. Get close enough, and the dust must vanish, leaving a dust-free zone around the sun. It was a straightforward prediction, and for 90 years, nobody could confirm it because nobody could get close enough to look. Parker's imager, an instrument called WISPR, saw it. As the spacecraft flew inward, the density of dust began thinning out, dropping away in exactly the way the models of vaporization predicted, extrapolating to a dust-free region within a few million kilometers of the Sun. A 90-year-old prediction, finally observed, essentially by driving into it. The second is the coronal mass ejection. On the 5th of September 2022, Parker Solar Probe flew directly through a powerful CME. Not near one, through one. And while it was inside it, its imager recorded something that had been theorized in 2003 and never confirmed. The CMI was acting like a vacuum cleaner. As it barreled outward, it was sweeping up the interplanetary dust in its path, clearing a path behind it, displacing the dust out to a distance of roughly 6 million kilometers from the Sun before it started to refill. Nobody had ever seen a CME interact with dust like that, and confirming it matters, because CME behavior is exactly what we need to model if we want to forecast when one is going to hit us and how hard. The third is my favorite because it was an accident. Parker uses Venus for gravity assists. On the flybys, its imager was left running, mostly to take opportunistic images, and on one pass, WSPR captured the night side of Venus and produced something extraordinary. Venus is famously shrouded in thick sulfuric acid clouds. Nothing in visible light sees through them. Radar sees the surface from orbiters like Magellan, but visible light does not. And yet WSPR's images showed surface features. Continental highlands, plains, plateau, visible as patterns of light and dark. The explanation is that Venus's surface is so hot, around 475 degrees Celsius, that it glows. Not brightly, but faintly, in the near-infrared and the very deep red edge of the visible spectrum, the same way a poker glows when you leave it in a fire. And WSPR was sensitive enough, and Venus's clouds were just transparent enough at those wavelengths to catch the glow of the ground itself through the atmosphere. A spacecraft designed to study the Sun accidentally photographed the surface of Venus in visible light for the first time, because the planet was hot enough to be its own light bulb. There's also a second spacecraft in this story, and the two of them together are doing something neither could do alone. In February of 2020, the European Space Agency, working in partnership with NASA, launched Solar Orbiter. It does not go as close as Parker. It does not need to, because unlike Parker, it carries cameras that can look directly at the Sun. Parker's imager has to point sideways, off to the side of the shield, photographing the plasma around the spacecraft. It cannot look forward, because looking forward means looking into an inferno that would destroy the optics instantly. Solar Orbiter, further out, can stare straight at the disk, and within months of arriving in the first close images it returned, Solar Orbiter found something new. All across the surface, at scales far smaller than anything previously resolved, there were tiny, brief flashes of brightness. The team nicknamed them campfires. They are miniature flares, millions of times weaker than the big solar flares that make the news. And they are going off everywhere, constantly, all over the Sun. If you have been paying attention, you will already see why that matters. Millions of tiny explosions distributed across the entire surface. Continuously injecting energy upward is precisely the nanoflare picture that one side of the coronal heating argument has been proposing since the 1980s. Solar Orbiter saw them from the outside. Parker measured the consequences from the inside in the switchbacks and the reconnection signatures. Two spacecraft, two agencies, two completely different vantage points, converging on the same mechanism from opposite directions. That is how this actually gets solved, not with a single dramatic result, but with independent instruments in different places arriving at a picture that agrees. And finally, the fate of the spacecraft itself, which I find quietly moving. Parker Solar Probe has now reached its final orbit. It has used its last Venus gravity assist, and it has no way to get closer and no way to leave. It will keep looping around the Sun, diving in and swinging back out, for as long as its instruments hold together and its power system works. Eventually, the systems will fail, the solar panels will degrade, the transmitter will go silent, and at some point the spacecraft will simply stop answering, but it will not fall in, and it will not burn up. It will keep orbiting. And here's the detail. The carbon-carbon heat shield is the most durable component on the vehicle. It is expected to survive long after the spacecraft behind it is dead. So what will remain, looping in toward the corona and back out again, over and over, is a dark, silent fragment of machinery hiding behind a shield that still holds, still turning its face to the Sun, for what engineers estimate could be millions of years. Long after everyone who built it is gone. Long after the mission is a footnote. A small, dead thing with a man's name on it, still orbiting the star it was sent to understand. And there is one last thing, which I think about more than any other detail in this mission. Eugene Parker submitted a paper in 1958 and was told by two anonymous reviewers that it was not worth publishing. The idea that the Sun was constantly bleeding a supersonic wind into space was, in the professional opinion of his peers, wrong. 60 years later, an object bearing his name was launched into that wind. 63 years later, it crossed into the atmosphere of the Sun and sent back the measurements that proved not just that the wind exists, but showed us where it is born, in the magnetic knots at the boundaries of the boiling cells on the surface of a star. He was 91 when he watched it launch. He said very little at the time. When asked what he was thinking, he said he was impressed by the rocket, and that all he could do now was wait for the results. He got some of them. He died before the rest arrived. The Sun is 150 million kilometers away. It has been there for 4.5 billion years, and it will be there for another 5 billion. And for almost all of human history, it was simply a bright thing in the sky that we did not understand at all. And then, briefly, in April of 2021, we reached out and we touched it.